All right, here we go. So we're going to learn about some other sort of more complicated versions of simple harmonic motion here. So we're going to learn about 4 other examples. Before you do anything, though, if you've not yet watched the video on that comes between 15.1 and 15.2, please take a minute to do that. It's like a 1-minute video about torsion pendulums. I do not have the equipment in my classroom to create a torsion pendulum, and so this is the only way you can see it. All right, so take a quick second and watch that video. All right, so the whole idea then with a torsion pendulum is you've got a spring, but the idea is instead of the spring bouncing up and down or vibrating side to side, it's more of a twisting motion. Okay, and so your object, you've got your spring that hangs down, and then you've got some sort of object. Maybe it's a disc or maybe it's a rod. All right, and so the idea is that rod is going to kind of jiggle back and forth, right? So it's going to go, and that is caused by the torsion created when you twist this spring or cable or whatever it is. Okay, and so the idea here is because we're talking about angular motion, right, rather than linear motion produced with a bouncing spring. What we're interested in is the restoring torque rather than the restoring force. All right. So remember that Hooke's law told us that the restoring force is proportional to the displacement. Okay. So it turns out you can also create a simple harmonic motion, and instead of having your object sort of undergo linear displacement, it can undergo angular displacement, and you still get simple harmonic motion if the restoring torque is proportional to the angular displacement. Okay, so I mean look, Hooke's law. All right, Hooke's law says the force equals to negative kx. So the force is proportional to the displacement. Right, here's your constant of proportionality. Right. Okay, so angularly, the angular counterpart to force is torque. Angular counterpart to position is angular position. All right, and so the idea is instead of using a letter K to represent our spring constant, we're going to use the Greek letter kappa, which I don't know how to draw. I always draw it like this. Okay, sort of a wonky K thing. I don't like that one. Let me do it one more time here. It's really meant to be more of a K. All right. So the idea is now your torque is proportional to your displacement. Okay. And they're in opposite directions, right? If you twist the thing to the right, the torque is going to want to pull it back to the left, or clockwise and counterclockwise. All right. So the big difference here is that when you talk about your spring constant, K, the units there are newtons per meter. Okay. Over here, our kappa, that's what this letter is, kappa, the Greek letter kappa. All right, it's going to be measured in units of torque per unit of angle. So it's going to be in Newton meters, torque, per radian. Okay? All right, but basically what this boils down to here is these torsion pendulums work exactly the same as a regular oscillating object, on a spring, with the exception that you're replacing all your linear values with angular values. All right, so probably we want to dive in and do an example. All right, so let me clear this off. All right, so check it out. Here's what we learned in the last video. In the last video, we learned that if you have an object in simple harmonic motion, we learned that the position at time t could be written as the amplitude times the cosine of the angular frequency times the time plus some phase constant, right? All right, well, for a torsion pendulum, you get almost the exact same equation, except you replace your x's with thetas, right? Because now we're talking about angular position, right? Okay, then if you take a derivative, we find that the velocity at time t is, well, you multiply omega times xm negative, right? Because the derivative of cosine is negative sine. Okay, now, over here, when we take the derivative, it gives us the angular velocity. So here's the problem, and this is super annoying, and I wish there was a better solution to it. that doesn't involve using a time machine, we now have two things that both represent, that are both radians per second, but they mean different things, okay? And unfortunately, what we've called omega in the past, we can't call it that anymore, all right? So for this chapter, omega is your angular frequency, all right? Weirdly, it's not necessarily the same as your angular velocity, okay? So remember, your angular frequency, oh shoot, is you're equating one complete vibration to 2 pi radians, okay? But if you've got, you know, that pendulum that I drew before oscillating back and forth, right, it might just go like this. The angle that it actually rotates through might not actually be 2 pi radians, right? It just might rotate from here to here, right? And so, you know, that angle, that's your theta max, right? Okay, so anyway, long story short, omega for this chapter is angular frequency, all right? If you want to talk about angular velocity, how quickly the angular position of your object is changing per unit time, the book actually just uses d theta dt, okay? And I've seen some books use the capital letter omega, all right? So, in the same way that kind of over here, velocity and angular frequency are not the same thing, over here, angular velocity and angular frequency are not the same thing. All right, so let's write these out. So angular frequency is this omega guy. Okay, all those omegas are angular frequency. All right, and then this dude up here, this guy is, that's the actual angular velocity, like we learned about when we were doing angular motion chapters ago. All right, okay, so let's clear up the clutter on the board here. All right, if you take one more derivative over here, you get the equation for acceleration at time t. Over here, taking another derivative gives you the angular acceleration at time t. Okay, and then, so what did we do over here? The next thing we did was we said, oh, well, we know that net force is mass times acceleration, right? So we took our acceleration equation and multiplied it by the mass to get an expression for net force. Over here, we're going to do the same thing, except we're going to use the idea that our net torque is I times alpha. All right, so the idea is your object that's rotating has some amount of rotational inertia, okay? And so if you multiply that by your angular acceleration, it gives you your net torque. The assumption is this will be, you know, your restoring torque, the torque from your spring or whatever. That's the only force acting on it, okay? All right, and so what we get then is this. So remember, this is our x, right? So here I've got torque equals this mass times x, right? I omega times x, right? Negative, okay? So we're just going to call this capital, okay? So this is equivalent to, here, sorry, I kind of jumped ship here. Let's go back over here. All right, so what did we do over here? Over here, we said that if you take another derivative, you get negative omega squared times x maximum times the cosine of omega t plus phi. And then we noted that, oh, well, this is just the same as x, so that's negative omega. Oh, sorry, nope, I'm ahead of myself, sorry. Okay, so that's that. So then you can find your net force by multiplying by mass. So force at time t is this times mass, so negative m omega squared x max times cosine of omega t plus phi. And now we said, oh, well, this is the same as x, so this must be our k, right? So k times x is our force at time t. So same exact idea over here. In the same way that we called this K, we're going to call this kappa. Okay? So now our torque is equal to negative kappa times theta at time t. All right? And when we did regular old simple harmonic motion, we learned that the period was 2 pi times the square root of m over k, right? Well, similarly over here, we replace m, which is inertia, with I, rotational inertia, and we replace k with kappa. Okay? And I mean, this is basically just the idea that your angular frequency is 2 pi over the period. So if you solve for the period, you get this. Okay? So, I know this seems confusing right now. There's all these letters, what's going on? Honestly, I struggled with this the first time I did it, and what I forced myself to do was just these simple harmonic motion equations on the left side of the screen make a little bit more sense because they're linear. So on the right side of the screen, it's all you're doing is you're replacing each of the linear values with its corresponding angular value. Okay, and just remember that the angular corresponding value for mass is inertia. K becomes kappa. Everything else is the same as we've been doing all year. Okay, so that is that. All right, so let's dig in and do an example here and kind of see how we can piece this all together. All right, so let's see. Let me get out a dual page here. Single page, embiggen. All right, so there's the problem that we're going to try to solve here. So we got a torsion pendulum consisting of a metal disc with a wire running through its center and soldered into place. So long story short, it's this thing like this. You got a torsion pendulum that looks like that. Here's your disc, here's your wire, it's soldered into place so that it doesn't move, or so that it doesn't slide on the wire. Okay. The wire is mounted vertically on clamps and pulled taut. Figure A over here gives the magnitude T, or tau, of the torque needed to rotate the disc about its center and thus twist the wire versus the rotation angle. The vertical axis scale is set by tau s is 4 times 10 to the negative third. At the top, I'll take that 4, I'm going to rewrite that. 4 times 10 to the negative third Newton meters. The disc is rotated to an angle of 0.2 radians and then released. Figure B shows the resulting oscillation in terms of angular position, theta versus time. So here's our graph. After you release it, that's the graph we get. Notice at time 0, our position is 0.2. Okay. The horizontal axis down here is set by TS as 0.4 seconds. So it looks like that's our period, right? So, what do we got? Let's, I guess, start by writing down some stuff that we know. Okay, so A wants to know the rotational inertia of the disc about its center. So it's a disc, which leads me to think, oh, well, the rotational inertia for a disc is 1/2 mr squared, but we don't know the radius of the disc, we don't know the mass of the disc. There are some gaps here. All right, so let's see if we can't go about this a different way. All right, so what's the purpose of this graph? Well, it's torque per unit, or I mean the vertical axis is torque, the horizontal axis is theta, and it's dealing with a spring. And I'm having a tough time processing all of this. So I'm going to ask myself this question. What would happen if I had a graph that looked like this, where I had the force exerted by a spring, not torque, but force exerted by a spring, as you stretched it through some distance and it gave a graph? Oh, well, that's just showing me Hooke's law. It's showing me that F is equal to Kx, right? Huh. Oh, well, over here in this graph, oh, this is just telling me torque equals kappa times theta. So let's pick a value of torque, pick a value of theta, and find kappa, right? In other words, look, what's this point here telling me? This point is telling me that if the torque I provide is this, then the displacement is this. So let's see, our torque we just said was 4 times 10 to the negative third Newton meters. That's acquired by twisting a wire with a spring, a torsional spring constant of kappa, through an angular displacement of 0.2 radians, right? So divide both sides by 0.2 and we can find out what kappa is. That must be why that graph was given to us, so we can figure out that little bit of information. All right, so if you divide both sides by 0.2, you find that your kappa is 0.02 Newton meters per radian. Okay, so that is useful information. All right, now what else? Let's see. Oh, we also know the second graph is telling us the period, right? Look, here's one complete oscillation that takes 0.4 seconds. All right, so let's do this. Let's give ourselves a little bit of room here. All right, so what have we figured out so far? We figured out that our torsional spring constant was 0.02 Newton meters per radian. And we know our period is 0.4 seconds, right? And we're trying to find I, right? So again, I'm still struggling with all these new equations. So let's think about what the linear counterparts to these are. So the linear counterpart to kappa would be K, period is period. Rotational inertia, that's the same as mass. Oh, well, we learned that the period of a simple harmonic motion thing is 2 pi times the square root of m over k. So torsionally, it must be this. T equals 2 pi times the square root of I over kappa. Oops. Okay, and that is, in fact, the same as the equation that we learned over here, right? Okay, so my point is, you're sort of not learning any new equations here. You're just making connections between what we already knew linearly and our angular stuff. All right, so here's my equation for period. Oh, and let's see, I know my period, I know my kappa, I can solve for I, right? Okay, so let's go ahead and do that. I mean, at this point, you can plug in the numbers, right? So what are we going to get? We'll do it in green here. So you're going to get 0.4 is your period. That equals 2 pi times the square root of I, which is what you're looking for, over kappa, which is 0.02. I'll let you do the algebra, solve for your I, and it turns out to be it's written right on the slide here, right? So it turns out to be 8.11 times 10 to the negative fifth. And remember, rotational inertia is kilogram meters squared. Okay? All right. So let's clear up the board a little bit and write down what we just learned there. All right, so we just found our I, and we got 8.11 times 10 to the negative fifth kilogram meters squared. All right, so then B says, what is the maximum angular speed, d theta dt, of the disk? So to be clear, this is what we usually would have called omega. It's your angular velocity. But remember, we're not using omega for angular velocity anymore. Omega is now angular frequency. So we're looking for d theta dt. All right, so there are a couple of ways of doing this. You can either do it using energy, or you can do it using derivatives, okay? And there's probably, oh shoot, time-wise, let's see, I'm gonna just do it using energy, okay? You could definitely do it using this, okay? You know your phase constant is, you know what, let's just do it. This is gonna be a long video, sorry, buckle up. All right, so here's what we know. We know that our theta at time t is theta max, oh, well, that's 0.2. Right, times the cosine of, well, let's see, omega is 2 pi over t, right? So that's 2 pi over 0.4, which is what, 5 pi? So 5 pi times t, And notice my phase constant is 0 because I'm starting at the max, right? Cool. Oh, this is actually not bad. So here's my theta max, right? And then remember, we know that, so remember we learned that V max was the same as X max times omega? Well, same idea, except we want to convert to angular, right? So d theta dt, that's our angular velocity, that's equal, max, sorry, that should equal to our omega, angular frequency, times theta max, right? So it's 0.2 times 5 pi. So omega is the 5 pi, theta max is 0.2, multiply it and you get pi. That's actually the way easier way to do it. You can also do this using energy, which is worth discussing. All right, so here's the deal with if you do it using energy. Right, so we know that for a spring, for a regular spring, U is 1/2 kx squared. Okay, all right, so that's for a regular spring. So that means that for a torsional spring, we're just going to replace all this with angular values. So it's 1/2 kappa times theta squared. Okay, so what we can do is we can say, all right, well, let's see. We know our kappa, right? Because we found it before. It was, what was our kappa? It was 0.02 Newton meters per radian times our, U max, sorry. Our U max is that, and then our delta, or our theta is 0.2 radians, so squared. So solidify that, and you will find that I didn't write out the answer to this. So what is this? No, grab a calculator. Sorry. 0.01 times 0.2 squared. So that gives you 0.0004 joules. Okay. Oh, well, so that's my maximum sort of elastic potential energy. Well, once it's unstretched, that all becomes kinetic energy, right? But specifically, it's rotational kinetic energy. So rotational kinetic energy is also that same value. All right, and then I know that RKE is 1/2 I times, now we got to be careful, it's not omega anymore, right? Because omega is angular frequency. We want d theta dt squared. Okay, so now we know what our I is. Let's do this. So do you want to do it? Yes, cool. So RKE is 0.0004. That's got to equal 1/2 times I. I we found before, and it was 8.11 times 10 to the -5th times d theta dt. Don't forget to square it below. All right, and so if you divide and then take your square root, your d theta dt gives you pi, it gives you 3.14 radians per second. All right. All right, there you go. Cool. Radians per second. All right, so that's sort of the premise behind this unit, is this idea of torsional simple harmonic motion, all right? And what this does is it allows us to deal now with pendulums, all right? And we are going to learn about, I said 4 types of motion, maybe there's only 3, so maybe we only have 2 things to do. Simple pendulums, oh no, 4, okay, got it. All right, so here we go. Next order of business. Oops. Where is it? No. Okay, so the next thing we need to talk about is what's called a simple pendulum. All right, a simple pendulum is a pendulum that basically has a particle of mass, m, It's called the bob, which is fun. All right, so you've got this particle of mass m called the bob suspended from one end of an unstretchable massless string of length L that's fixed at the top point, okay? And so to calculate the period, it turns out that the period is 2 pi times the square root of the length divided by the acceleration of gravity. All right, so there it's just kind of plug and chug. All right, where does that equation come from, though? All right, so the equation can be derived 2 different ways, regardless. Oh, you know what? I skipped an important thing. There's one other fact about a simple pendulum. Simple pendulum consists of all this stuff up here, and the angular displacement, max, has to be small. All right, in other words, you can't pull this thing all the way back up to, you know, like 50 degrees, okay? It's got to be for a small angle, all right? Otherwise, this equation here does not quite work, all right? So this is only for small theta max, okay? And so the reason for that is it relies on sort of a calculus-y math fact, which is as follows. It turns out, for small theta, it turns out that the sine of theta is equal to theta in radians only. This does not work in degrees. Okay, so for very small angles, if you measure in radians, the sine of an angle is basically equal to the angle itself. Okay. So how do we get this equation? All right. So one way to do it is by considering the restoring torque. All right. What we're going to do is this. We're going to say, all right. So here's our pendulum, right? It's got this angle theta over here. All right. And so the idea is it's this force of gravity here which produces the restoring torque, right? Okay, so our restoring torque is the torque from gravity, and so that torque is, well, it's F times D times the sine of theta, right? So our F is the force of gravity, our D is the distance from the pivot point, which is just the length of the rope, times the sine of, well, it's technically this angle, okay, but it turns out that the sine of theta is the same as the sine of the, what is it, supplementary angle, right? Like if you've got 30 degrees or you've got 150 degrees, those both have the same sine value, right? So whether I do this angle or this angle is the same, and so that is theta, all right? And so then the idea is we're going to, because our angle is small, we can replace this with theta. So this is a thing you need to know how to do. I've seen this question on AP exams before. So please make sure that you are clear with this idea that sine theta is equal to theta for small theta. Okay, so our torque due to gravity is now Fg times L times theta. Oh, well, L is a radius, right? So this just becomes a jumper. So L theta, let's see, remember, x equals r theta, right? So this is my radius, this is my theta. So this is just the x. It's the distance that you've pulled it back. Technically, it's along the curve. Okay? So, oh, no, that's not the way I want to do it. Sorry, I'm getting ahead of myself. Pretend I didn't just do that. Sorry. We're talking about torque, aren't we? Sorry. So we want to show that the torque is proportional to the theta, right? Well, these guys are constants, right? So there you go. So we're going to call that kappa. So the torque from gravity is kappa times theta. Okay, and I guess technically negative, right? Because if you pull it clockwise, the restorative torque will pull it back the other way. So I should probably have negatives on all of this. Okay. Oh, and we learned. So this means then that kappa is FGL. Oh, that's the same as mg times L, right? Okay. All right, and now we know that the period of a thing undergoing a torsional restorative force is 2 pi times the square root of I over kappa. All right, so 2 pi times, well, what's the rotational inertia of a pendulum? Well, it's a point particle with inertia mr squared. Oh, better yet, how about ml squared, since our radius is L, right? Over kappa, which is mgl. And notice the m's cancel, one of the l's cancels, and so you get 2 pi root L over g. Okay, so that is one of the two ways to prove that relationship. Okay, now the other way you can do it, if you so choose, you know what? I don't think you need to know the other way. That's probably just as good as anything. There is a way to do it, thinking about it in terms of the restoring force, but I think the way I just showed you is probably the easier way. So I'm going to leave it at that. All right, so there you go. So that's a thing you should know. Period of a simple pendulum, right there. There we go. I'm going to skip the other proof. All right, there you go. All right. We're going to skip that. All right, now, here's the other type of pendulum. You can also have a pendulum where your mass is not all concentrated at the end. So picture like a baseball bat swinging back and forth about the middle, right? Or like your leg. Well, that's not a perfect example. But when you walk, if you swing your leg back and forth, your leg is kind of a pendulum. But not all of the mass is down at your foot, right? Okay, and so it turns out that the period of a physical pendulum, that's the name for this, okay? Notice not all of the mass is concentrated at the end. So it turns out that the period of it is this mass, okay? And the proof for this is almost the exact same thing as what we just did in option 1. The question, though, is what is H, all right? So to be clear, I is the rotational inertia about O, where O is the point about which the pendulum is pivoting, okay? And then H is the distance from O to your center of mass, okay? It's the distance from O to your center of mass, okay? It's kind of like the H in the parallel axis theorem, right? It's how far you're moving your axis of rotation from your center of mass, okay? So that's how you find the period of a physical pendulum, all right? And then sometimes you'd be interested in what's called the center of oscillation, all right? The center of oscillation is, it's the point P where we need to place a bob with the same mass as the physical pendulum to make a simple pendulum with the same period as the physical pendulum. All right, so imagine you've got a baseball bat. Okay, you drill a little hole right here and you let it swing back and forth like this. Okay, that's going to swing back and forth with some period. All right, I've already forgotten the name because it doesn't come up very often. The center of oscillation represents, suppose I had a physical pendulum. All right, and it swung back and, a simple pendulum. So this is physical, this is a simple pendulum. All right, so suppose I've got another simple pendulum that swings back and forth with the same period. All right, this length here is, well, I guess, yeah, I don't want to say that. So the length to this point here, and then if you measure down the length L, this point here, P, that's called your center of oscillation. This point is the center of oscillation. All right, so I'll do an example where we find a center of oscillation here in just a minute. Okay? So I think that's the next slide, hopefully. Yes, here we go. All right, so we've got this physical pendulum. It consists of 2 meter-long sticks joined together as shown in the figure at the right, okay? So you've got 1 meter stick going this way, another meter stick going this way. It's pivoted right here, so it's basically, I don't know if it's going to let me do it, kind of swinging back and forth like this, except unlike my drawing here, this point here is staying fixed, so it's kind of like, and then oscillating back and forth, okay? So, it's one rigid object rotating back and forth, all right? So we got to find the period of oscillation about a pin inserted through point A up there at the top, okay? So, the first thing I need to do, so the period of a physical pendulum is 2 pi times the square root of the rotational inertia of the thing over mgh. So the first thing I'm going to do is find I. So I for the blue thing is 1/3 times the mass of the stick times this distance squared, which is 0.5 meters. Okay? Plus the rotational inertia of the red stick, which is 1/3 times the length of the whole thing squared. Okay? And so you can look back at your rotational inertia equation sheets that I've given you for that. So this gives you 1/12 plus 1/3 is 5/12. So I'm going to just write this as 5/12. No, 5/12 m, my bad. Okay, so that's I. All right, so the next thing we need to do is we need to figure out where our center of mass is. All right, so the center of mass is going to be determined by the fact that I've got a mass m up here, and then another mass m here, but the center of that can be treated as being right there, right? So, how do I want to do this? Let's do this. Okay, so let's see. So the position of our center of mass is, well, it's the mass of the top stick, which is m, times its position, which is 0, plus the mass of the bottom stick times its position, which is basically 0.5 meters, right? Because it's 0.5 meters down. Okay, all divided by our total mass, which is 2m, right? Because mass plus mass, right? M plus m. All right, so the position of our center of mass ends up being, well, it's the m's canceled, so you get 0.5 over 2, so it gives you 0.25 meters. All right, and so that is h. Okay, so now to find the period of this thing, I'm going to do 2 pi times the square root of I, so that's 5/12 m, over the mass of my thing. Now this, be careful here, when I wrote up my solutions I actually got this wrong. M here represents the mass of the whole thing. For us that's 2m, right? Because we've got 2 meter sticks both of mass m. Okay, or at least that's how I solved it, right? I assumed that the mass of each stick was m. So times 2m times g times h, which is 0.25 meters. Shoot, we've got all these, some of these m's are meters. So that, all the other m's are mass. Okay. Meters. So if you solve this, you get 1.83 seconds. So that is the period of this thing. All right? So the last thing we got to do is find the center of oscillation. So the question then is, well, if it was a simple pendulum, the period would be period equals 2 pi times the square root of length over g. Oh, and I know that my period has to be 1.83, so I'm just going to solve for the length now. Okay, and solve for L, and you end up getting 0.83 meters. Okay, which means that my center of oscillation is 0.83 meters down from the top. Okay? All right, and then finally, so let's see, we've done torsional pendulums, simple pendulums, physical pendulums, and now the last thing is we got to talk about pure circular motion, uniform circular motion, okay, which let's see. So here we go. All right. So from math class, you have hopefully learned that you can write a circle using polar coordinates so that the x-coordinate is r cosine theta and the y-coordinate is r sine theta. I guess that's not polar coordinates, but so you can write your x and y coordinates that way, right? All right, now another thing that happens to be true is it turns out that sine of theta is the same as cosine of theta plus pi over 2, okay? Which is why the graphs look so similar, right? One is just a shifting of the other. Oops. Okay, so a circle can be thought of simple harmonic motion just on two separate axes. It's basically a, what is it, parametric equation, right? So here's the equation on your x-axis, r cosine times omega t, and then your y-axis is that with a phase shift, okay? And notice, because it's a circle, your maximum x value and your maximum y value are both equal to your radius, all right? And it turns out that your angular frequency is the same as your angular velocity, all right? So if you need a visual, here it is. All right, so if you look at, let's see if I can get rid of one of these. Oh, whatever. If you look at the green circle, for example, the outer circle, you can see that down here, this green dude here and this green dot that's going back and forth above it, those represent the x motion at time t, right? And over here, this green dot that's going up and down and up, that represents the y motion, okay? And so now I would just say, oh, well, I know my position at time t is x max, which is my radius. So let's just call it r cosine of omega t. And over here, my y value is just a shifting of that. So it's r times the cosine of omega t plus pi over 2. Or I guess you could just call it r times the sine of omega t equivalent. Okay? There you go. What do we do? 42 minutes. Well, it's going to have to do.